Hi everyone. Today I'll be live solving the 2021 January Silver contest for USACO. So there's 4 divisions. Silver is the second one. It's usually one of the easier ones. Since it's only the second one. So I have not seen these problems before, and I'm in plat right now, so this shouldn't be too hard. Since silver is two divisions down, but we'll see. So I'll start a stopwatch, and then we'll just go. Okay, start. Problem 1. Farmer John's cows are showing off their new dance moves. So there's N cows stand in a line with cow I at the I position line. The sequence of the dance moves is given by K pairs of positions. Okay. Um, in each minute of the dance, the cows in positions AI and BI swap. The same K swaps happen again in this, then again in this, and then okay. So it's a cyclic fashion. Okay. For each cow, determine the number of unique positions in the line. Okay, this seems pretty standard. Okay, so basically, I think we can probably model this as some sort of graph. Because we're basically swapping these cows, and then since it continues indefinitely, we can sort of like use some DFS thing to find the components. I think. I'm not sure. I'll try to map out the sample. Okay. Okay, so our sample is okay. So we have 5, 4, 1, 3, 1, 2, 2, 3, 2, 4. Oh shoot. Okay. Let's write it here. 5, 4, 1, 3, 1, 2, 2, 3, and then 2, 4. And I guess they start out at line. So yeah. So they start out as just like this 1, 2, 3, 4, 5. Okay. So after the first minute, we're swapping 1 and 3. Okay, so we're gonna swap this, and then we're gonna be swapping 1 and 2. Then we're gonna be swapping 2 and 3, and then we're gonna be swapping 2 and 4. Okay. So that's after one iteration, and we just continue doing this forever. So let's see what happens when we do this. So after 1, 3, we have 3, 2, 1, 4, 5. Then we have 2, 3. I'm guessing the 1 and 2 are the positions, right? The positions. Okay, so it's this, then 2, 3 swap, the 2, 1, 3, 4, 5, and then 2, 4 swap. So 1 and 4 swap basically. So 2, 4, 3, 1, 5. Okay, that's after one iteration. Let's just do this once more. Okay, and so far position this cal 1, it's been in position 2, and position 4. And I'm pretty sure it's going to go to position 3 next time, because the cow in position 4, which is 4, it went from 4, 4, 4, 2. Okay. And then the cow in position 2 went from 2, 1, 1, 1. And then the cow in position 1 goes from 1, 2, 3, 3. So like basically over here in these four, since like the nice thing about this problem is that this happens basically indefinitely. So it happens forever. Um, so I'm pretty sure this cow, like cow 1, at some point in time, since it goes on till infinity, it's going to end up in one of these positions. It's not going to ever end up in position 5, because 5 isn't ever swapping with any of these things. So I guess we just have to calculate the size of this component. Um, and oh shoot. Okay, cow 3. It only ends up at 3 positions. It ends up at 1, 2, 3. Oh, okay. So I guess it doesn't end up in all the positions in its component. So we have to figure out which ones it does. Um, okay. So let me try to map this out better. So cow 1, it goes from position 1, where we started out like this. So it goes from position 1 to 3, to 3, to 2, and then to 4. Okay. the cow in position 2 goes 2 2 2 1 2 1 2 1, and then after since this goes on forever, this is going to basically start at position 1, so it's going to go through all of these, and then cow 3, it ends up at position 3, right? So it goes from 3 to 1 to 2 to 3. So cow 3 basically visits 1, 2, and 3, and then it stays there. It starts at position 3 again. Cow 2, it goes from 2 to 1, and I'm just ignoring overcounts. And then it goes from position 1 later. So we have to calculate basically from where 1 starts. This is cow 2, this is cow 3. Cow 1. Cow 1 goes from 1 to 3, and then 3 again, and then 2, and then 4. Okay. And then cow 4, it's going to go from 4 to 4 to 4 to 4 to 2. 4, 4. So it goes from 4 to 2, basically. And then it's going to end up in 2's position. Okay. So I have to figure out a way to calculate all of these components quickly, since n is 2 times 10 to the 5. Okay, I guess like these middle places aren't important because we're doing cycles of k steps. So we want to calculate at the beginning and at the end for each, I think. Yeah. That should be the move. So like basically the beginning for 3, it goes from 1 to 3. Or it starts at position 3, sorry. This starts at position 3. Cow 2 starts at position 2, and then yeah. Okay, so cow 3, it starts at position 3, and then it ends up at 3. And it visits 3 of them in the process of this. Cow 1, it starts at 1 and it ends at 4, and it's going to visit 4 in this process. And then 4 goes from 4 to 2. And then 2 goes from 2 to 1. And so I guess we're basically going to form this sort of like, or this is same edge. We're going to basically be forming these cycles. And they're going to be forming these nice cycles because there's only going to be one cow at each spot, and these cows are going to form a permutation. And so we have to calculate the number of cows visited in this cycle, which is basically it's not just the size of the cycle because we also visited cow 3 in between. So I guess if we keep the sizes of each of these, if we keep the sizes, then maybe we'll be able to do something with that. Why is it so hard? Okay. I guess like the total number of things in a cycle is going to be the union of all its elements. So how many total elements will we have? If it's O of n squared, then we can't use this approach. But I feel like, would it be O of n squared, or would it be we're only really updating an element when it changes position, right? So we're going to be doing this like 2 times k times, I guess. So 2k plus n, because each starts in position whatever. I think this is like our bound on the number of elements we'll have in our sets. So there's 4 plus 2 plus 4 plus 2. That's 12. Yeah, and and then 5 also has 1. Yeah, okay. So that's like a total of 13 elements, which is basically 2k plus n. Okay, so I guess we can sort of like implement the first process naively. Then we'll create cycles, and for each cycle, the number of times it visits, it's going to be the union of it's the number in the union of these sets. So I'll try to implement that. This is silver. Okay, I'll take the input. And just take this in as pairs. I'll use zero indexing, so I'll just subtract one from each of these. Should do this. Okay, and then I'll create basically some sort of, how are we gonna do this? Should I store it in sets? Nlog should probably be fast enough for this, right? I guess I could use sets. If it time limit exceeds, I can probably use some sort of like ordered pairs or ordered sets, I guess. Okay. So this is an array of size n. We start out, all of them start out with their original one. Let's create a have. Okay, so they all started at the original position. So we'll just insert I into each of these. And now we have to do all our swaps, right? So I'll just do this. And we're gonna swap the elements at positions A and B. Okay. I'll create a vector that stores a current permutation. Permutation. Okay. And then this is gonna be the identity permutation. Okay, so when we're swapping these elements, we're storing these positions and the elements that they go to, right? 1, 3, yeah. So the element in position, and I'll just call this left, or let's call this first and second. This first element is going to be current of A, since A is its position, and then second is equal to current of B. So now, first we'll insert second, I guess, because yeah, because that's gonna get second now, and then half second will insert first. And then we have to swap them. So swap current A and current B. Should work. Let me print out all the sets. Okay. Okay, let's see how this goes. So 1 visits 1, 3, 4. That seems wrong. 1, 3. I missed a 2 somewhere. So okay. Oh wait. So let's analyze this. So positions 1 and 3 first. So our first element is current of 1 and second is current of 3. And then we're gonna insert second here. So 1 will insert 3, right? Yeah, and then 3 will insert 1. Okay, and then we're gonna be putting 1 in 3's position. They're gonna be swapping this. Let me print out the final permutation. Okay, so this says we're ending with 2, 4, 3, 1, 5. Okay, that's correct. Why is it printing this wrong? So 1, 3, 4. It's missing the 2. 1, 3, 3, 2, 4. 1, 3, 3, 2, 4. Maybe I'm let me print this after every step. So 21034 is basically 32145. 23145, 21345, right? Then 24. Okay. This goes in 3324, yeah. Should be like a 1. Um hmm. Okay. Oh, maybe I have to enter the positions, not the values. So I should be going B with an A maybe. See how this works. Okay, I think this is more accurate. So this is 1 is 1324, which is yeah, okay, 1234. And this is gonna be 1, 2 for 2, so that's correct. For 3 we should be getting 1, 2, 3, and then 4 we should be getting 4, 2, which is 1, 3, 1, 0 index. Okay, so this part is correct. Now we have to run a DFS. I have to create like an adjacency list too. So this adjacency list will just help me map our permutation elements to each other. Since we want to map these final ones. Yeah. Okay. So the total number of insertions I'm going to be doing here is just 2k. And then we're doing n insertions here, or over here. So we'll have an O of 2k plus n elements, which is O of k plus n. Okay, so let me now create the adjacency list. Adjacent current I. So we have to get the position at which this ends, right? Okay, and so this 1 should map to 4 and 4 should map to 1. So okay. Yeah, okay. I don't know why I was blanking. Okay, now we just have to run recycle stuff. So you visited. Device DFSI. We don't need a parent. We just need this. So for everything in its, you want to insert that into in or her elements. feel like this is an overkill solution. I don't know. It just feels really annoying for its silver problem. I should probably make this a global thing. Okay. Not visited next. Then we want a DFS on next. Then I'll create an answer. And then so for true, and I'll create a vector of elements that we're putting index in. And this is going to take the current index. Okay, so now for everything in here, you want to set the answer of that to be equal to the size, current element stuff size. And I'll clear this before I do this. And then we should go to print it out. Okay, let's see if this works. Ah, what is this? Yeah. Let's see this. Okay. We should have the correct cycles. This out. Courage. Yeah. I kept outputting the wrong sizes. Okay, sure. That works. Yeah. So this is right. These sizes are correct. So maybe my index in is wrong. But yeah, I should probably clear this. I need to clear this too. Okay, that makes sense. Cool. Let's see if this works. If it PLEs, then I'll have to use unordered mapper or some other hash function. Where's USACO? Okay. Maybe you might. Okay. Okay, this is fast enough. Yay. I felt like that took really long. Okay. So we got all 20 cases. Nice. We took like 24 minutes so far. Let's move on to number 2. I'll explain the solution more in detail later if you're wondering. So I'll just move on to number 2 for now. Bessie has recently received a painting set, and she wants to paint the long fence at one end of her pasture. This is n consecutive 1 meter segments. She has 26 different colors available. This looks cancer. A through Z in increasing order of darkness. A is a very light color and C is very dark. She can therefore describe the desired letter she wants to paint each fan segment as a lengthened string, where each character is a letter. Okay, yeah. All of them are uncolored. She can color any contiguous range of segments with just single color and a single brush stroke. Okay. As long as she never paints a lighter color or darker color. Okay. She has to leave some consecutive range of fan segments unpainted. 2 candidate ranges. For each candidate range, what is the minimum number of strokes? Paint each fan segment outside of those in the range with its desired color, leaving all such segments inside uncolored. Okay. This is like similar structure to a like recent code forces problem. So basically I think what we're having is we're given this string and we're given like a consecutive range that we don't want to paint, and then we want to find the minimum number to paint. So obviously we can probably separate this into a prefix and suffix, right? And then for each prefix we can count the number that we need to paint that, and for each suffix you have to count that. So for like 3, 6, 3, 4, 5, 6, it takes 2 strokes to paint AB, and it takes 2 strokes to paint CB. So that's 4. And then for 1, 2, 3, 4, I guess we put A, then B, then C. So I guess we want to find the minimum number of yeah. Okay, so we want to find the answer for a given prefix, right? So we have to see how we want to do that. So basically we just have to solve this answer for a given string quickly. So let's say we're given some string, S1, S2, and these are all letters. So if this has any A's, I guess, then all the A's we can always print in one stroke, if there's any A's. And then for the B's, so like if we have A, B, B, A, B, A, since these B's, since they cover this, like, they go over an A, and so we can't paint a lighter color over a darker color. So this is going to take at least 2 strokes to paint the B's. And then for the C's, it's a similar thing. The C's, the number of times you have to paint a certain letter is the number of connected components if you ignore all the dark things. So like the reverse of this would be the number of times if you start from C, the number, or like, yeah, so like the number of times you paint Z is the number of connected components that Z has. And then the number of times you paint Y is ignoring all the Z's, the number of connected components of Y's you have, where a Z can equal to a Y. So I guess you want to use some sort of like we want to count the number of components after like adding or removing edges. And I guess it's optimal, or it's easy to add here because you can probably use something like a DSU, which is disjoint set union maybe. So like for this example, let's see. So we have like BB and then B. So right now this is 2 components, and I guess we can always connect this edge together. And so we have 2 components. Then we're going to connect this B to A, and then this B to A, and then this B to A, and then this B to A. Because these B's don't matter anymore, since we're going to be painting the A first anyways. So we're going in reverse order. And then the number of components here is just going to be equal to 1. Okay. So for a given string, we want to count that. But we also want to count this for all prefixes. So you might have to do something like DP. Yeah. Let's see what we can do here. So we have A. So that's just 1. AB is obviously going to be 2. And that's because B is different from A. And B is not like the lightest character there is. And then ABBA, or ABB, This letter is equal to the previous one, so it's just the same. For A, B, B, A is equal to the lightest character. So the answer for here is just equal to 2, I guess. And then for an A, B, B, A, B, this would probably be what, 3, right? Okay, so like let's take in like so when we take in a new letter into our string, if it's equal to the previous one, then our answer doesn't change. It's just the same. If it's greater than the previous one, then like this, we'll probably have to add 1. Do we always have to add 1 though? Yeah, I think we do always have to add 1. So before +1, I'll just write a +1 here. And if it's less than the previous one, then what options do we have? Like over here, it stayed the same, but does it always stay the same? So like if we put a C over here, that's going to be 3. And if you put a B, would it stay the same? So we would paint, or no, it would have to be different because we paint these A's first. And then since like from this one to the last occurrence of B, there's a larger letter in between. So if it's like less than the previous, if there's a larger, or if there's a smaller, sorry, if there's a smaller letter in between, then we add 1 letter in between this and last occurrence. This and last occurrence of that. Then we add 1. Otherwise, we stay the same. Okay, so since there's only 26 letters, this could be done with the set or something. So like basically, we're gonna store the last, as we go through a prefix, we're gonna be storing the last occurrence of each letter. And then when we're adding a letter in, we basically find if there's a smaller letter than that in between it and its last occurrence. And if there is, we'll add 1 to the answer. Otherwise, we'll just stay the same. And so to find whether there's a smaller occurrence, we can just query all other 26 ones. So yeah. It shouldn't take too long to code up. And then we have to do this for suffixes too, obviously. Okay, we'll do our computation first and we'll answer all the queries. So I'll store an answer for prefixes and then suffixes. Prefix 0 is obviously equal to 0, and last occurrence, all these letters, or yeah, or whatever. We want to set all these to probably like something greater than n at the beginning. Yeah. Okay. Let me set this to +1. Now, as we're moving forward, this is our current thing to add, our current letter. So if we haven't occurred in X yet, we haven't seen this yet, meaning it's n+1, we're gonna have to add 1 to the answer, I think. Yeah. Then dpi, we're doing this 1 indexed. Let me do this. Okay, then dpi is equal to dp of I-1, or not dp, this is prefix of I, equal to prefix of I-1 plus 1. Otherwise, int y equals 0, y less than x, t equals last occurrence of y. And if that's greater than or equal to the last occurrence of x, if that's greater than the last occurrence of x and less than I, then we're gonna have to change it. Okay. Then instead of boolean, add equals true. And equal prefix I minus 1 plus add. Okay. I think this works. Oh, then we have to set it, obviously. Yeah, okay. Now let's do this for the suffix. I'll make this n plus 2. And suff of n plus 1 is 0, since there's nothing there. So let's just do the same thing again. Now let me set all the things in last occurrence is 0, or -1. If -1, then 1, otherwise. Basically do the exact same thing. If t is greater than the I, and t is less than last occurrence of x, add equals true. Suffix I is equal to suffix I plus 1 plus add. And last occurrence of x is equal to I. Okay. Now we can answer our queries. So this is going to be equal to pref of a minus 1. This is the first a minus 1 letter, plus a suffix of b plus 1, I think. Before we do that, let me just check that this function above works correctly. See the prefix values. Shoot. Oh yeah. Okay, print it all zeros, what? And Q. It only print 2 values. Good. Why is it only doing 2 values, huh? N is equal to 8. QH. Oh, we're probably getting some sort of error loop thing. Otherwise, the error is probably here. Oh, wow. I wish they really did lowercase letters. I think it might be this. Yeah, okay, so 1, 2, 2, 2, 2, and then 3. Yeah, 4, 4. Okay, that makes sense. Suffix should be probably works then. Maybe you want to print this. Let's see this. Zero, 3, 6, 1, 4, 3. Okay. Let's hopefully this works. And what is the time complexity? This is just like O of n times 26, which is fine. Yay, okay, it worked. Okay, 40 minutes so far. Number 3. Pasture is represented. Okay, so he has a picture of cows grading their pasture to hang on his wall. The pasture is represented by an n by n grid of square cells. Picture an n by n chessboard with 2 less than or equal to n less than or equal to 1000. In the last picture he took, his cows were too clumped together when reaching the pasture. So he wants to make sure they're properly spaced out, and he therefore insists on the following rules. No 2 cows must be placed in the same cell. Okay, so 1 cow per cell. Every subgrid of 2 by 2 cells must contain exactly 2 cows. Oh, okay. So there are no other restrictions. You may assume that Farmer John has an infinite number of cows available based on previous experience. This assumption. He wants some cells to contain cows more than other cells, in particular he believes that when the cow is placed in cell ij, the beauty of the picture is increased by a of ij units. Okay. So I guess we have to look at this 2 condition first, since that's a bit weird, and we want to kind of incorporate our beauty things after that. So let's basically analyze what grids we could fill. Create this 4x4 grid, and I'll just mark them with X's if there's a cow there. So let's say we place a cow at the bottom, the top left. We either have to place a cow here, here, or here. So if we place it here, then we have to place 2 cows here, and we have to place 1 other cow here. Okay, so we cannot put a cow here anymore. And so we have to place a cow here or here. So we place a cow over here, then we have to put 1 other cow. And then over here we need 2 cows. Let's say we do it here. Okay, then this is filled, this is fine. Then we can do it here. We can't place it here. We could put 1 here. We could put 1 here. Okay, so it's formed this like sort of series of X's. There's probably other ways to do that though. Shoot. We can't place a cow here or here. Okay, so if we place like a cow in these 2 cells, then we have to put a cow in these 2 also, because this is going to be already have 2 cows, so we can't put 2 cows here. And then we have to put 2 cows, and then this like after that is the same thing. So if we place 2 cows like this, then we have like, this is sort of like the first 2 rows are set. Okay. So let's look at the 3rd row. Now if we place a cow over here, then it's the same condition as the first 2 rows. So we could either put it here, or if we put it over here, which is the only other spot, then I think we're gonna fix these two rows also. Because if we put it here and here, then this is gonna have to go here since we can't have 3 cows. Okay, so that's fine. If we put like this. Otherwise, at the beginning, at the second cow, if we put it in the top left and we put the second cow here, then this cannot contain any more cows. So we have to put one cow either here or here. So if we put a cow over here, this works out, this works out. Then we have to put a cow over here. So we can't put it here. And we have to put one in this box. So let's say we put it over here. So this works, this works, this works. Then over here, we have to put one more cow. We have to put it over here. And then we don't put anything here, we don't put anything here. And then like we're sort of back at the same position after that. So it looks to me like we sort of have kind of rows of 2 to fill out. 2 each. Is n even in this? Oh, it's not even. Okay. But basically like these 2 rows will determine this next row. And then that's going to determine the row after that. And then that's going to determine the row after that and so on. So we really only have to focus on the first 2 rows, I think. Yeah. Or we have to do like this in blocks of 2. Yeah, if we do this in blocks of 2, so we'll focus on these first 2. And then we can focus on these next 2 because this will be already determined. I guess it's going to be identical to the first row. So let's look at what blocks we can form if we only have 2 rows. So we put something here, and if you put it here, we have to put something here like this, and so on. So that's filled out. Now if we put something here, well then these columns will be filled out. So that's going to be kind of like deterministic in a sense. And then if we put something here, we could put something here now. And then we'd have to put something here after that. Yeah. And I guess this would have to go like this. This would have to go like this. Okay. So if we fill out the first 2 rows, then everything else will be determined. So we have to I think there are only a few states really that these rows can have. Or if we place something here, I guess from our observation earlier, the third row is going to be the first, same as the first. Or is there any way to prove this? If I proved it, I think I'd feel more at rest. Okay, so this cow or this cell, this grid or this square, sorry, this is gonna have 2 cows and this will also have 2 cows. So if I make the third different and then I do this, or well, it is possible for its third to be different, isn't it? But then if this third row is different from the first row, then the third column will be the same. So we're either going to have to focus on rows or columns. And I feel like we can, without loss of generality, just do rows, and then we can sort of like rotate our grid and then focus on columns. So for rows, when we choose a cell, we'd have to choose this, and then the fifth, and so on. Okay, so I guess when we enter like this column, this like column will be uniquely determined by the previous column, right? Or not uniquely determined, but it might be determined. Like if the previous column is empty, then we have to put all x's here. Otherwise, we'll have to put if there's one x here, we either put an x here or an x here, and then we can sort of use the dp to do that. So like each state will store the maximum score you can get based on the first n columns. And so dpi, I guess like dpi would be you're at the ith column and you have like a bit mask of j, a mask of j. So like a 1 1 would indicate two x's. A 1 0 would indicate one x over here and then no x's over here. And so we can either go from like, if we have 1 1, then we have to go 0 1. If we have 1 0, we can go 1 0 or 0 1, and so on. See if that works on the example. So like we can take this, then we have to take this. Yeah, so like in the sample, this is the same as this. And then this is the same as this. So second and fourth rows match. So like if the first and third rows don't match, then I think the first and third column will match. So we'll solve this for like this grid. And then we'll solve it for the opposite one. Or sorry, for it rotated 90 degrees. It feels so weird. It feels kind of sus. Expanding our values in. And let's create a DP. Okay. And then since we're assuming the first and third row, first, third, and fifth are all equal, and then second, fourth, sixth are equal, etc. We can create like, we can compress this into like a 2D or 2 by n grid. So I'll do this. We have 2 rows and n columns. So okay, so I guess we can do this. Val of ij equal to a of xj is 0 first. We can do our dp. So how do we want to do this? So I guess we have to find a recurrence relation for the dp. So instead of so let's define our dp as you're at the ith row and you fill it with this mask. So dp of I mask is basically equal to dp of I minus 1 new mask. And then this has some possibilities. So if this is like 1 0, this can be 0 1 or 1 0. If it's 1 1, then we can have 0 0 and etc. And then we're going to be adding the values for here. So if mask and 1, I'll throw I, otherwise. And okay, so this yeah. It's like our recurrent relation. Add. 1 minute. We look at this case. It's 1 0. So then you put a 0 1. And then we can put a 1 0 here. So then this row will be uniquely determined. Yeah, okay. That should work. Equal to okay. And we'll do a case for I equals 0. I equals 0. Then dp of I mask is just equal to add. Okay, so that's for like assuming the first and third rows are equal, and then fifth rows is equal to the third, and so on. So let's just print the value here. If n minus 1 mask for I, which is our current mask. And then we'd have to rotate this grid and then solve it for the other case. Yeah, so that's solve it for this. So now if we have the first and third columns equal, how do we have to rotate this? It's just going to be a transposition, right? Like, let's just look at this. A9, A10. Okay. A of 16. So this is like our first case where this is equal to this, and then the second is equal to the fourth. Our second case is when this first column is equal to the third column. And so we want to use this same algorithm as before. So we'd have to transform this first column into a row. Yeah, so then basically if we define a new matrix, A prime of I of j, is equal to A of Ji. So let's do that. I'll call this B. A of ij is equal to A of Ji. And then we can just run this exact same algorithm here. So we'd obviously have to change all our A's to B's. So this is going to be to stay the same. It's going to be B over here now, I think. Anything else dependent on A? I don't think so. And then print our answer. Hopefully this works. I'm still kind of like unsure about this algorithm. It seems really weird. Well, if ij. Okay, let's see what it runs for this. Come on. Oh, it worked. Thank God. Okay. So we stopped. We finished with just over 1 hour on the clock. So 1 hour, 1 minute, 40 seconds. And we got all of number 3. Okay, before I end this video, I feel like I did a really bad job explaining. I'm also really tired right now for some reason. So I'll just explain these problems briefly. So number 1, oh shoot. Okay, number 1, basically you have your n cows. And you have the sequence of positions. Okay. Yeah, okay. So you have the sequence of positions, right? And basically, if you look at this first cow, let's just focus on cow 1. Cow 1 goes like eventually to some other cow. Let's call this A1 and then A2 and then, or I don't want to use A since that's giving the input. We'll call this X. So we go to like X1 to X2. And we're going to end at XI or like XR after like K moves, right? Or I'll just call this XK. So cow 1 ends at XK. Cow 2 ends at like another sequence of YK and so on. Right? So we have this like sort of abstract thing, but we can take this further because if we look at cow XK now, cow XK will go to some other cycle. Let's go Z1, Z2, and it ends at ZK. And then this cow ZK, it's going to end somewhere else and so on. And so basically you can prove that if you could make a graph between the starting and ending positions, it's going to form a bunch of cycles because these will always form like some sort of permutation, and you're going to have one outgoing edge and one incoming edge off each vertex. So that's going to be a cycle. And so basically the answer for the cycle, the number of cows it visits, is a union of all the cows over here. Because let's say if one eventually goes into X of K's position, it's eventually going to go through all of this sequence, and it's going to eventually go through all of Z's sequence until it comes back to one sequence. And so that's why we have to take the union, and it's similar for all the other elements in the cycle. So we do this separately for each cycle, and then we just print out the answer. Number 2, I felt like was the easiest problem on this. So basically you have this like fence, and you're given a bunch of candidate ranges, and you want to find the minimum number of strokes to paint each range if you're given this unpainted range. So you're given like the string si plus 1, and then sj, then sj plus 1, and so on. Okay. And so you're gonna be told that this is gonna be unpainted. You can't paint over this, so you can separate the problem now into just a prefix and a suffix. And if you calculate the answers to all prefixes and you calculate the answers to all suffixes, then you can solve the problem. And so the answer to a prefix is basically, since we're calculating the answer to prefixes, it might make sense to look at the previous prefix. So like when we're adding another letter to the prefix, when you add a letter, basically the answer is either going to change by 0 or 1. It's going to change by 0 if, say, you have a C and you have like a D, E, C over here. It's going to change by 0 over here because you're going to be painting all the C's before you paint all the D's or E's or F's, because you can only paint darker over lighter. So you want to go from light to dark. And so you're always going to do this first. And because there are no B's or A's over here, you can always paint this with this last C. You can always just extend the range, because when you paint the D or E later on, it's just not going to change anything. But if there's a B over here, you cannot paint this C with this C. That's going to paint over the B. And if you come back to paint the B later on, you cannot paint lighter over darker. So you basically just find whether there exists a letter that's less than this, that occurred between this and its last occurrence. And if it does, you're going to have to add 1 to the answer. Otherwise, you just keep the answer the same. So that's your motivation for prefix. Suffix is very similar. Problem 3. So problem 3 was like interesting. I feel like I got really lucky on this. If I got a wrong answer, I feel like I'd probably be spending another 2 hours on this or something. But basically, I guess like you just have to play around with what types of things you can get. Whenever you have super restrictive conditions, it always makes sense to look for some sort of pattern. This condition is very restrictive. There's really not much you can work around with this. So you just look at this. You play around with this condition, and what I found was either the first row is equal to the third row, is equal to the fifth row, and then second is equal to the fourth, and so on. So either this holds for rows or it holds for columns. It holds for either one. And so basically there's only 2 cases after that. You either hold this for the rows or you hold this for the columns, and then you can use some sort of DP from there. I don't know why they put a DP problem in this. I'm interested to see what the official solution is, whether it's DP or not, because this is really this is a classical sort of bitmass DP problem. Let me actually see what the solution is. Because if I recall correctly, they don't put DP on silver. Okay, so this is basically what I made. So how did they do this? Start from either column. To solve the colors. Oh, there are only 2 of them, huh? Oh, is it alternating what? Oh, okay. So I guess there's probably some sort of alternating condition. Well, I overkilled number 3 then. But the main idea was the fact that you can only have the first row equal to the third row, equal to the fifth row, and so on. So that's number 3. I'll look at the other solutions later. I think I'll end the video here. So thank you for watching. If you enjoyed this video, please like and subscribe, and share with your other friends who took the 2021 January Silver contest in case they're interested in seeing this. That's